All right, today we're diving into the world of smart factories and a pretty cool new AI approach that could seriously change how they work. We're going to be looking at something called dynamic multi-objective scheduling, which is a system designed to solve a massive headache in modern manufacturing. So I want you to picture being a factory manager. Every single day, you're faced with this fundamental choice. Do you crank up the machines to full speed to get products out the door, or do you slow things down a bit to save energy and be more sustainable? It's this constant balancing act, speed versus sustainability. And that balancing act leads us right into what you could call the scheduler's dilemma. I mean, how are you supposed to manage these competing goals when they are both absolutely critical to your business? On one hand, you absolutely, positively have to meet your deadlines. It's the lifeblood of the business, right? It keeps customers happy, keeps the company profitable. But on the other hand, there's this huge push to save energy. And it's not just for the environment, it's also about lowering your operating costs. And here's the real kicker. These two goals are almost always pulling in opposite directions. You can usually get a task done really fast, but it'll probably guzzle energy. Or you can do it slowly and be super energy efficient. Getting both at the same time? Nearly impossible. And this is the exact kind of complex trade-off that we're now asking AI to help us solve. So naturally, we turn to AI for an answer. But the traditional approach, using what's known as reinforcement learning,
in RL, the standard method is rigid. Let's call it RL-SR.
which stands for Reinforcement Learning Sum of Rewards. The way it works is you basically tell the AI to chase a single combined reward. You might say, okay, AI, your final score is based 90% on hitting deadlines on time and 10% on saving energy. The AI then gets really, really good at maximizing that one specific blended score. That sounds pretty reasonable, doesn't it? But it opens up a huge question. What happens when your priorities suddenly change? What if there's a sudden energy price spike or a supercritical rush order comes flying in? And this is where the old RL-SR method really falls down. If you want to change those weights, say, shift from caring mostly about speed to caring mostly about energy, you have to retrain the entire AI model from scratch. This is incredibly slow and super expensive. It also means AI engineers, not the actual factory experts, have to guess the right balance way ahead of time. The source paper even calls this a semi-blind manual process. It's just not flexible at all. This inflexibility just screams for a better way. And the new solution is actually brilliantly simple. Instead of a rigid formula, it uses a much smarter system that's based on an auction. Now, this is a really fundamental shift in thinking. The old way, RLSR, used one generalist AI agent chasing a single premixed reward. The new way, called RLSB for sum of bids, is completely different. It creates multiple AI specialists. One becomes an expert in speed. Another becomes an expert in energy efficiency. And instead of chasing one reward, they now make separate bids for each job. This whole system is called auction-based online scheduling, or ABOS-RL. And you can think of it just like it sounds. Every time a new task needs to be done, the machines in the factory hold a little auction. They look at the task and then place bids to see who should get to do the work. And here's a peek at how that auction actually works. When a task becomes available, a machine collects observations, things like the processing time it needs and how much energy it would cost. Then its AI specialists calculate bids. And from there, it's simple. The system just finds the machine with the highest bid and gives it the task. Simple, but very powerful. So the really cool part is how this works with multiple objectives. When a new task pops up, the AI specialists on each machine make two separate bids, one for how fast they can do it and another for how efficiently they can do it. Then, and this is the absolute key, a human manager sets the weights right there in the moment. They can say, you know what? Today I care 80% about speed and 20% about energy. The system then combines the bids using those live weights, and whichever machine gets the highest final score wins the job. This all sounds great in theory, but, does it actually work? Well, the researchers put it to the test to see exactly how this new RLSB model performs in the wild. First up, they tested it in a static scenario, using that same 90-10 preference for speed for both the old and new methods. And the results show that performance is basically identical. The new RLSB approach performs right on par with the old RLSSR. So the big takeaway here is you don't lose any raw performance by switching to this more flexible system. But that was never the point.
The real magic, the entire reason for this new approach, is that you can now change those weights on the fly, anytime you want, with absolutely no retraining necessary. And here is the proof. Check out this chart. It shows exactly what happens when the manager starts changing priorities. Along the bottom, you can see the weight, or importance, given to saving energy, increasing from left to right. And as the manager tells the system to care more and more about energy, what happens? The total energy consumed, that's on the vertical axis, it just drops significantly. The system responds directly and predictably. And here is the other side of that exact same coin. As the importance of energy goes up, the importance of lateness, or, finishing on time, naturally goes down. And just like you'd expect, the average job lateness starts to creep up. This is the trade-off in action, and it proves that the manager now has a real, tangible control knob to balance these competing goals in real time. And this brings us to the most important takeaway from this whole explainer. It's all about putting the human expert back in control. 0. That's the number of times you need to call up an AI engineer and spend weeks retraining this model just because your factory's priorities shifted for the day. The power to adapt is now instant. The researchers really put it perfectly. The AI is used for what it's good at, optimizing a single, clear goal. But the human expert, they retain the strategic control, deciding how to mix and balance those goals to navigate the messy, unpredictable real world. It's a true human-AI collaboration. And that leaves us with one last, really provocative thought. This idea of creating AI specialists and then letting a human expert mix their advice in real time is incredibly powerful. What would happen if we applied this same model to other complex fields? I mean, what if a financial advisor could dynamically adjust an AI's strategy, balancing aggressive growth against risk tolerance based on a client's needs that very day? The possibilities, they are really fascinating to think about.